How are we doing on mass spec? Any questions about mass spec? Okay, let's look at where we left off at substitution reactions. I think we're looking at nucleophiles. Sterics can negatively affect the nucleophile. Makes sense, yeah. More crowding is going to be more difficult to do a backside attack. The two molecules to come together in the bimolecular rate determining step. We can have substitution, for example, on the nucleophilic nitrogen. More substitution. Tertiary amines typically are non-nucleophilic. They can still be bases. Because the base, when it acts as a base, the sterics doesn't affect that. We'll see triethylamine used as a base in E2 reactions. I just gave you the elimination handout. Substitution could also be not on the actual atom that's a nucleophile, but it could be next door, like in this example. But this also leads to crowding. It's not perhaps as bad as if it was on the oxygen. You cannot have two bonds to oxygen and still be a negative charge, but it's adjacent, so there's still lots of crowding that can still inhibit that from being a good nucleophile. And indeed, tert butoxide, which this is called, is often used as a non-nucleophilic base for E2 elimination. Is that better? Okay. Okay. Sterics. What about resonance effects? A conjugated or delocalized lone pair is not as reactive, but can still react, particularly when it's an anion. Which is more nucleophilic, okay? The way we're talking about, I think we're talking about mainly SN2, but it can apply to SN1. The problem is SN1, the nucleophile is not involved in the rate determining step, so why would you even consider it, really? Rate doesn't affect it. Mainly we talk about SN2, right? And we're mainly talking about the nucleophile attacking such a carbon with a leaving group and kicking this off, which is going to be more active, more reactive, more able to attack it. But the compound that is more minus, the more minus you have, the more it's going to be attracted to the partial plus. This is a localized anion. There's no resonance. This is delocalized. We have resonance here, right? We can do resonance structure. Yeah? And we can move the lone pair onto this oxygen, the charge onto that oxygen. Yeah? Resonance structure. The true structure is thus what? Partial minus and partial minus. It's actually very symmetrical. Each oxygen has a partial minus. Either one you look at, partial minus, that's only a partial minus. You see how it's only a partial minus? The structure says full minus. Well, that's because you got a no resonance, right? That's a full minus. Which is going to be more attracted to it, a full minus or a partial minus? Full minus. Full minus, yeah. This is more reactive than that. A conjugated delocalized lone pair is not as reactive. Okay, localized lone pair. What about that lone pair? Resonance, it's conjugated. We can also say the lone pair is in a p orbital. Typically, a lone pair in a p orbital is not going to be that reactive towards anything. It's busy doing resonance. The extra lone pair here is in a p orbital. Lone pair in a p orbital. Lone pair here is in a hybrid, sp3. Not delocalized. Isolated, more reactive. So this amine is more reactive than the aniline towards an SN2 substitution. Hybridization effects. This nitrogen is more reactive than this nitrogen. Why? That's right, hybridization effect. This is sp3, and this is what? sp2. That's the difference. More reactive. This lone pair is held tighter to the nucleus. That also somewhat quenches the lone pair. I mean, the lone pair is closer to the positive nucleus. Charges are closer together. That's kind of quenching. That's lowering the energy of the system. This lone pair is more out there, higher in energy, more able to make a bond and do a backside attack. So there's no resonance here. There's no resonance of that lone pair. It's common for students to think that's in a p orbital and there's resonance just because there's pi bonds close by. No. That lone pair is not in a p orbital. Okay. Most of that correlates with same thing, acid-base chemistry. Which is a stronger base, left or right? That one, stronger base, stronger base, stronger base. Strength of nucleophile correlates with strength of base, but not always. Again, sterics. Which of these three is the strongest base? No, the one on the far right is the strongest base. Strongest base, right? It has more donation. It has more electron density on the oxygen, stronger base. But it's the weakest nucleophile. Why? Because sterics significantly affect nucleophile strength. There's others that are kind of do not correlate. F minus versus I minus. Which is a stronger nucleophile, better nucleophile? I minus? Anybody agree? I minus? Why is I minus the better nucleophile? Which is a stronger base? F minus is a stronger base. Why?
More stable.
Because F minus is less stable. Okay? Conflict. Okay? That's a big conflict. I minus is a better nucleophile. We said why? We said nucleophile. We described what the better nucleophile is on the previous page or two. Okay? And that statement did not apply to bases. Okay, nucleophiles. Okay, let's rank these from weakest to strongest. Group 1. What's the weakest nucleophile? Of course, these are all minuses, right? You can get rid of the so minus, yeah? Which is the weakest? Water, why? It is neutral. Weakest, water's 1, being 1 being weakest. Which one's next? Well, let's look at these two. S minus or O minus? I'd rather be going from strongest to weakest. It seems like that would be better. Which one's the strongest here? That's nucleophile. S minus. Why? Same reason. I minus is better nucleophile than F minus. Why? Bigger. Bigger atom. Electrons more out there. Better nucleophile. But that's a stronger base. Why? Because that's more stable. Less stable. This wants an H more to go back to neutral. That's more stable. If it's more stable, how's it a better nucleophile? See, there's some conflict there. Okay? Better. What about OAC? What is an OAC? Acetate, right? Which is a better nucleophile, left or right? Right. Right. Right is correct. That's delocalized. That's more of an anion. We just did that above. So if we rank these from worst, what's the next worst? 2, then 3, then 4. I need to turn that around. I'd rather go the other way. The best there is the S minus. It's better than O minus, and O minus is better than this O minus because this one's delocalized. And water's the worst. At least this is an anion. An acetate anion is going to be a better nucleophile than neutral water, neutral oxygen. Even though it's delocalized, it's still an anion. You can try number 2 on your own. Summing it up, what type of nucleophile can participate in an SN2 reaction? Talking about strength, and the answer is strong only. Only a strong nucleophile can participate in an SN2 reaction. Why? Mainly because the nucleophile is involved in the rate determining step. Correct? Since the nucleophile is involved in the rate determining step, it needs to be strong enough to do something. Because the rate determining step is the difficult step. That's why it's rate determining. You've got to have a strong nucleophile to do an SN2. What nucleophiles are strong? I mean, we can rank them, but of these 4 up here, which are strong? Well, we need to state that. strong ones. Which ones are strong? Very much like strong bases. Strong ones are going to be anions or sp3 amines, or strong nucleophiles. Okay, what's a strong nucleophile? Anion or sp3 nitrogen? We got to be careful though with this kind of opening statement. Not all anions are strong, just like with bases. For example, Cl minus. Yes, it's an anion, and so we may say it's strong, but it's not that strong. It's quite stable. It's the conjugate base of the strong acid. Just like it's not a strong base. Strong bases, I think we said anions and sp3 nitrogens. But Cl minus is not a strong base, even though it's an anion. I mean, it's the conjugate base of HCl. It wants to exist as Cl minus. That's why HCl is called a strong acid. Okay, so there are exceptions, but that's the opening statement. Anions and sp3 amines are your strong nucleophiles. Okay, practice. Which compounds below are strong nucleophiles? Is that a strong nucleophile? No, it's not an anion and it's not an sp3 nitrogen. No. Can it be a nucleophile? Yes, it can be. Strong nucleophile? No. Strong nucleophile? Yes, this is organic chemistry. Get rid of that. Okay. You know that's ionic, right? I know most of you know it's ionic. All right? Everybody should know it's ionic. For some reason, every week I get lab reports that shows KOH like this, or sodium hydroxide like that. Sodium hydroxide is not ionic, right? Wrong, it is ionic. Okay? No. Potassium and sodium does not make a covalent bond. Not in Gen Chem, not in this class. So that's strong. How about this here? Yes. sp3 nitrogen, strong. Here. No, lone pairs in a p orbital. The electrons are delocalized by resonance, not strong. KCN, one of my favorite reagents. KCN. What is this? Cyanide, right? Strong or weak nucleophile? Strong, yes. Water? No. We circled the three strong nucleophiles. Anions, sp3 nitrogen. Only the three circled can do an SN2 reaction. At least in this class. In all serious, guys, a number of you need to pay more attention to ionics, okay? And realize they're ionic. I see too many of you just not know how to deal with an ionic. I probably disagree with how they're taught. I don't know why. Apparently you guys are taught that it's covalent until it dissolves or something. I don't know. I don't agree with that. It's always ionic. If anybody has anything that you can tell me about your understanding, I don't quite get it. It's always ionic. It just seems like you guys are taught that it's not ionic in some cases. If that's the case, I'd like to understand. Okay, let's look at examples of SN2. Some examples and some terminology. What can we do with SN2? What type of functional groups can we make? Number one, alkylation of oxygen. Okay. Carboxylic acid, alkylation of carboxylic acid. It's A here. We got a carboxylic acid. We can make esters by alkylating the oxygen. Is this a good nucleophile for SN2? No, it's neutral. We first have to convert this to the anion. Now we have a good nucleophile. How would you convert this to the anion? What would you react this with? What? Strong base. What's your favorite strong base? Okay, NaOH. We can do that. This reacts with the carboxylic acid to give this plus what? Plus water. The sodium sits with the carboxylate anion. Yes. Now we have a good nucleophile. What's the equilibrium here? Well, this is about 5. This is 16. Which side's favored? 5 or 16? 16? Okay. So you chose a base that's going to give the desired anion fully at equilibrium, or essentially full. I mean, the difference is 10 to the 11. That's 100 gazillion. Okay, so at equilibrium, you got 100 gazillion of these and only one of these left. I consider that pretty much complete. So good choice of base. Now we can come in with some type of carbon leaving group, such as that, right? Tetrahedral carbon leaving group. Now we can get a reaction and these electrons can come in here and kick off the leaving group by SN2. We can make that bond there. And there we go. We just did a good reaction. But we first had to convert the acid into a good nucleophile. Okay? Let's first make the oxygen anion. SN2. We converted the acid to what functional group? It's now an ester. What type of group did we put on the oxygen? In general, an alkyl, specifically an ethyl. We put an alkyl group on the oxygen. Alkylation of carboxylic acids. That's what we just did. Okay? So we can make esters from acids by this route. Alkylation by SN2. Next, alkylation of alcohols and phenols. Sodium hydroxide. Happens to be the same base you suggested for above. Can we use sodium hydroxide to deprotonate this? Because that's not a good nucleophile. Will this reaction work? Well, this is 16. That's 16. Which side's favored? Neither side. And if neither side's favored, your equilibrium ain't going to work in practice. All right? You got to have about 2 or 3 pKa units in your favor to work in practice. Okay? No, sodium hydroxide is not strong enough to do this. Here again, many of you guys, when you're taking a test, are not going to realize that's O-. All right? You got to realize it's O-. Everybody agree? It's O- and sodium plus? All right? What's the difference between these two? absolutely nothing. I just did not show the sodium up here. And I showed the charge. But just like if I showed this here, sodium chloride, that's sodium plus and Cl minus, right? Okay. You can also show, that's kind of like formula there. All right? Just like that's formula. It just happens that something has more over here. But it doesn't mean there's no charge here. I just haven't shown it separated. Just like with sodium chloride, I could show it like that, we know what it is. Or I could come over here and show it like this. But these are the same thing. It's just that looks like formula, and this looks more like structure and more detail. Okay. Not a good base. What base will work? We can use sodium metal. Now, sodium metal is not actually called a base. It's sodium metal, metallic sodium. But it will work as a base. If you take an alcohol and react it with sodium, you will get the what? This thing. What do we call this thing? Have we used this terminology before? What functional group is this? Alcohol. Yes. What do we call this here? Let's do it this way. What's the name of this? Hydroxide. So what do you want to call something that has an alkyl group? Not hydrogen oxide, hydroxide. What is this? That's an alkyl group. It's called an alkoxide. Okay? If you treat an alcohol with sodium, you will get the sodium alkoxide plus hydrogen gas. Okay? If you want to balance that, you can. It's not balanced right now. But that is a common reaction. It's not really an acid-base reaction, although it did remove the H to give the anion. It's really a redox reaction. And we're not going to be able to do an acid-base mechanism because sodium doesn't even have a lone pair. It's a radical reaction, most likely. It's redox, to simplify. The sodium is 0 here, that's the oxidation state. Now it's +1. The H is +1 here, but now it's elemental, so it's 0. So you have redox going on. If you take an alcohol and put sodium in it, it will start bubbling. What are the bubbles? Hydrogen gas being formed. We may do this in lab this week. Cut some sodium. Anybody ever cut sodium before? Did y'all do this in Gen Chem? No? So it's a very common way to make the alkoxide from the alcohol using sodium metal. All right? The outcome we want, but by a redox reaction. Now we can think about doing chemistry here. Okay, you have an alcohol, treated with sodium, you get the alkoxide. Now we can come in with a tetrahedral carbon relieving group, such as benzyl chloride. And now we have a good old SN2, and we just made that bond, yeah? And if you want to balance this out, what else is formed here? Just to show it. We'd have sodium chloride, right? But there's a sodium sitting here, right? And then Cl minus leaves. We've got sodium ions and Cl minus ions. We can show that pair together. If it's dissolved, it's all ions. If it precipitates, then it can be maybe a solid, an ionic solid. Okay, so what are we doing here? We're first making the good nucleophile. Then we're doing an SN2. We converted the alcohol to what functional group? Alkylation of the alcohol gives the ether. Yes. This is called a Williamson ether synthesis. Whenever you essentially alkylate the oxygen of an alcohol to make an ether, it's called a Williamson ether synthesis. Of course, you first have to make the anion, because the neutral alcohol is not a good nucleophile for SN2. You can also do this with phenols. Take phenol. Here you can use sodium hydroxide. Yes, you can use that. Why? This is 10, this is 16. Which side's favorite, 10 or 16? 16 by 10 to the 6, a million. Okay, that's a good equilibrium there. What do you want to call this here? The phenol phenoxide. We call them a phenoxide. So phenols, you can use hydroxide base. Alcohols, no. And so we can do the reaction down here, sodium hydroxide. Then we can come in with maybe methyl iodide. And we can do a alkylation of the oxygen, yeah. Active carbon, kick off the iodine leaving group. Now I'm showing this is sort of two separate steps. It is two separate steps, but you may see this written like this. 1, sodium hydroxide. 2, methyl iodide. The 1-2 approach in terms of showing a multi-step line reaction, right? And of course, I'm using sodium hydroxide here. You can use potassium hydroxide, lithium hydroxide. Hydroxide's hydroxide. Question?
Yes, if on a test we're given a different hydroxide, will we be given the pK values?
What do you mean? Hydroxide reacts with this to make this plus water. Water 16, no matter what.
Okay.
No matter what the cation is. Sodium has nothing to do with this being 16.
I'm referring to the initial pKa.
Sodium has nothing to do with this being 10. That's a phenol.
Okay.
Cation has nothing to do with the pKa's. At least nothing significant at all. Making rings. Look at this reaction. If you take this compound here and treat it with sodium, you get that ring compound with an oxygen in the ring. You see what's going on here? What's sodium going to do to this? Oh, here. What chemistry do we know? Sodium reacts with the alcohol to give what? To give the alkoxide. Yeah? That's what we just did on the previous page. And once you get this, what can it do? Internal SN2. Intramolecular SN2 to make this ring. So the oxygen bonds to a carbon over there. We made that bond right there. Or you could show it on the other side, no different. What else is formed in this reaction that we did not show up there?
Yes.
Yeah, hydrogen gas. And you're going to have to balance that because we've got two H's on the far side, but we only have one H on this side. Of course, the balancing is only for your stoichiometry. I mean, hydrogen is hydrogen. It's forming hydrogen. Yes, it will form hydrogen, it will form sodium bromide, and it will form that product. In terms of molar amounts, you're going to have to balance your equation to get that. Synthesis. Whenever we do synthesis, typically we're looking at a target product, and we want to go backwards, and we want to say, how would you make this? Well, how would you make it from a Williamson ether synthesis? Provide a Williamson ether synthesis for this compound. What are the components of a Williamson ether synthesis?
To make that an alcohol.
What are the components of a Williamson ether synthesis?
Sodium.
Somebody?
Sodium metal.
I would call that a reactant. It's not a required reactant. I'm getting at what are the two core components of a Williamson ether synthesis? What?
Alcohol and phenol. You start with one of those two, and then you move on.
That'd be one of them, alcohol or phenol. But I would call it more the alkoxide. The alkoxide, and then what other component do you need? We did it 2 or 3 times on the previous page. We also did it up there, but both components were in the same molecule.
Leaving group?
Yeah, the alkoxide and the carbon with the leaving group. That's the two components for the SN2 Williamson ether synthesis. Now, how do you make the alkoxide? You can react an alcohol with sodium metal. You could also use potassium metal. There's other metals you could use. So, what we need an alkoxide and we need a carbon with a leaving group. Okay, so show the two. What alkoxide would you use and what carbon with a leaving group would you use? Basically, we got to break the molecule down to go back to 2 smaller components. Break this apart into the alkoxide and the carbon with the leaving group. Somebody got it?
I reckon it's the same.
Over here. Uh-huh. Uh-huh. It's good. There's actually 2 choices. There's actually two choices. Okay. Mm-hmm. Yeah. Yeah. Anybody else? What bond do we want to, or we're going to make in the Williamson ether synthesis? That bond there? We're going to make that bond in this synthesis?
No.
That bond there? My partner just joking. Hopefully you know we're going to make maybe that bond. Between the oxygen nucleophile and the carbon with the leaving group, right? Okay. But we can also do it over there. Let's call that A and B. A, let's back up. Backing up is a retrosynthesis arrow. I think we've maybe done this before. We're going backwards. We can go backwards to that anion, which is one of the components we need. And what's the other component? That would be this portion over here. Then this 3 carbon, that's going to be what? Right there, right? We just need 3 carbons. Henry, what's wrong with this? Well, those, oh, let's go forward. This is going backwards. We're going to say we're going to back up. How do you make a car? We got a car. How do you make it? Let's back up to a frame, 4 wheels, an engine. Okay, we're going to back up to the components. Retrosynthesis. Now let's come forward. Will these react to give this? What's going to be the reaction? Oxygen will just make bond here? Good. No, no, no. I've seen this answer before though. No, this means that this is going to bond here and kick off an H? I don't know. Because there's 3 H's on the end. There's only 2 on there. No good. What do we need on this end carbon? A leaving group. What's your favorite leaving group? How about a tosylate? Tosylate? How about that? Is anybody's favorite leaving group a tosylate? Thank you. Okay, we can propose this. Now, will this react to give this? Well, let's think mechanistically. This could attack here, kick off the tosylate. This is A, right? Will that give it that A bond? Okay, how about the B root? We can also do it on the other side. What would that involve? That would involve, somebody got it? I'm going to do bromine. That's my favorite leaving group. Plus what? Plus this. We back up to that. Does that look good? Would that give the same molecule by making the B bond? Yep. We've got 2 different roots. 2 different possible Williamson ether syntheses. Which root do you like best? Why do you like A best? You just do. No reason, but you just do. Leaving group is on a primary carbon. Over here, the leaving group is on. Yeah. You could then also say, well, over here, the nucleophile doesn't have any, it's only monosubstituted on that carbon, where over here it's disubstituted on that carbon. So you could argue both ways. The main consideration here is leaving group on primary carbon best. Okay, this is best. LG on primary carbon. That should be the best. Particularly once we start understanding and learning elimination reactions, which is in the blue handout. Okay? This over here, more prone to an E2 elimination. Okay? Let's put that in your notes for now. The best here is leaving group on primary carbon. It's going to be the best for an SN2. Okay? Have to make choices. There may be other reasons to guide your decision when you have choices. On the back of this handout, there's a number of homework problems, okay, including asking you to do a Williamson ether synthesis. Please be looking back there. I know some of you have already been looking back there because you have been asking questions. We just did oxygen as a nucleophile. What about sulfur? Sulfur would be analogous to the oxygen. If it's a neutral SH compound, you need to make the anion to make it a good nucleophile. One comment about sulfur is your body uses sulfur as a nucleophile. Your body uses sulfur a good bit for different things. you're exposed to an electrophilic toxin such as methyl iodide, you know that's carbon iodide bond here. Very toxic, causes SN2, attack the carbon, kick off the iodine very easily. Toxic stuff, methyl iodide. Your body has a protective mechanism for this. Glutathione, it's a tripeptide. And it has, one of the residues has a sulfur. And under certain conditions, this may be an anion. But sulfur is a good nucleophile. Better than oxygen. But it's larger. Less electronegative. And this, it may be an anion form. This will attack here, kick that off. And that's okay. That's the purpose of glutathione. It's there to protect you from bad stuff. Problem is your body will run out of this, and if you get too much of the bad stuff. Okay. If you overdose on Tylenol, it forms a reactive electrophile. They give you this to treat the overdose. It has a nucleophilic sulfur, and it reacts with the electrophilic metabolite of Tylenol. Sulfur is acting as a nucleophile here. Okay, your body uses it, or doctors use it. Sulfur's a good nucleophile, better than oxygen. Okay, guys. I think we need to have a quiz on mass spec. See how we're doing on mass spec. We'll have a quiz on mass spec on Wednesday. Just mass spec. Just mass spec. Okay, guys, have a good day.